All right. All right, guys. Oh, yeah. So obviously we're going to eventually go over that handout from last time. So if you did not get that handout from last time, make yourselves known. Okay, so for right now, stop looking at that for a second. I mean, I wanted you to kind of look at it, see if anything looks familiar, just to get a little preview of what's going to happen. And now I want to kind of break down the important parts of it. They're all important, but the most important part of this idea. One flaw that confidence intervals have, even if you account for not knowing the real standard deviation, one flaw that they have is that they're built around a sample mean or sample percentage. You guys kind of with me? A little bit? So, for example, I did a quick analysis, and let me see if I remember the numbers because I didn't write it down. 26 people in here filled out the survey, and they said that they had a credit card. The mean, let me see if I remember this. The standard deviation of the credit card debt was actually like 1,600 something. And the mean was 1,329 in credit card debt, which is completely understandable. My entire graduate existence was funded by plastic, so it took me a while to pay that back. If I created a confidence interval for this, I'd have to first tell you that credit cards are about normally distributed. They're not really normally distributed, but once you get up to this, 30 is the magic one that works for anything. The more normal that your distribution starts off as, why did I say off like that so weird? The more normal it starts off as, you can take a smaller and smaller sample and it would still be okay. If it started off really crazy, you'd have to have 30 or more to be sure that you have it normal enough. But if it starts off normal, I don't care how small your sample is, right? So it's normal enough that I can take 26 and then that'll be good enough. You guys kind of with me? A little bit? All right. The rest of you just go with me. So we could create a confidence, let's say like a 95% confidence interval. Right? So how do you do that?
So when you divide the 5% by 2?
Good. I like it.
And then you get the z-score? T-score?
I like it. Dissension in the ranks. There's 2 scores you can choose from, and this is what those of you who weren't here last time missed out on. You're going to love this. I love it. We don't know the population standard deviation. If I know sigma and it's normal, I can use z. If I don't know sigma, if I only know s, but it's normal, I then have to use t-scores. I love it. If you weren't here last time, you're like, what? Anybody need a t-score chart? One of them up here? T-score chart. Okay. So if you weren't here last time, you must go look at the video from last time. You desperately want to do that. It's not actually that difficult. Let's all remember how to use this thing together, or learn how to. So the first big thing is to remember, or suddenly know now that this is the first you're hearing it, sigma, z-scores, s, t-scores, but they both have to be normal to do anything. All right, good. This chart is the t-score chart. It's crazy. Where are z-scores on the t-score chart?
On the bottom.
At the very bottom. So the bigger my sample gets, the less I need what t-scores do for me. T-scores are always bigger than the actual z-score would be, but the bigger my sample gets, I need that less and less and less. That's why these numbers go down and down and down. It's almost scary how much sense that makes. Okay? Or you're like, I'm not scared at all. It doesn't make any damn sense. What would my degrees of freedom be for this problem?
25.
Good. Degrees of freedom is always... Oh, neat. I was like, how the hell does that happen? Magic. I was kind of hoping it would be. Degrees of freedom is always one less than your sample size. Okay? So I know it's degrees of freedom is 25. It's off the chart there. How much area will be in the tails?
0.5.
0.05?
0.01. Oh,
0.05 because it's 95% inside. If you went to one tail that's 2.5%, it's still the same color. Kick ass. So the chart's trying to make you go to the right place no matter what. And I stop at
2.06.
I love it.
0.06.
2.06. So now I know my t-score is 2.06. Then the formula is just about the same, really. It's the mean, give or take, some score times some standard deviation divided by the square root of n. The formula doesn't really change. Is that I use a t-score instead of a z-score. Ooh. So now you just plug and chug. Try to finish it out real quick. So my suggestion is, of course, do the error first. So does somebody have that yet? What's the error?
654.88.
Do it one more time.
654.88.
Is that cool? Is that what you guys are getting?
Yeah.
Okay, good. That's crowdsourced. I like it. And now you just add it, subtract it, and you get your interval. And that interval is...
74.12.
Say again? Sorry?
674. One of them is 674.12. And the others. Yep.
Is that right?
Yep.
Okay.
Yep.
Now, considering that you guys are a bad sample, right? This is not a really good confidence interval if you're trying to say something about all college students or whatever, right? But we'll just look past that for the moment, because you are the sample that I have to work with. So what does it say then?
95% confident that the intervals.
What does it mean?
We are 95% confident.
All right, we are 95% confident that this interval will actually catch the real mean. Now, I don't know if anybody, I don't blame you if you weren't, because y'all like stats is freaking weird. Just tell me what the hell's going on. But I don't know if anybody was concerned with the fact that I built this around not mu, but x bar. So the real mean is right there, and it's normally distributed around it. It was normal enough anyway. You guys kind of with me? So I can construct it. I know that 95% was the mean though. X bar could be who knows where, but we still went up and down and we caught. So confidence intervals, the one problem they have is they're built around sample data. So there's still something about them that's not quite 100% correct, especially when I'm trying to test a claim. So I could say, does it look like the average credit card debt for statistics students would be $2,000? Your confidence interval would say, no. There's evidence in your confidence interval that it's not. What's probably you're wrong?
5%.
5%. Because 5% of the time, your confidence interval will not catch the real mean. You guys kind of with me? That's how this all kind of comes back. They are not really good for tests because they're built on X bar. So I'm trying to get us into next chapter. Where the nice thing with these are they're quick. I can get them very quickly, and they're still useful. They still mean what they say. But they're not strong enough evidence when I'm trying to test claims. How are we doing so far? I don't know if any of you get that at all, but I'm trying to build up why Chapter 8 exists. So, before we get into the technical details on that handout, I want to get the idea behind Chapter 8. So, let's see. Let's say that somebody had a claim. Actually, we'll use the same data. I'm sure somebody's got that data written down that I just erased. No? Crap.
Yeah.
Yep. Data.
Which?
And equals 26?
Yep.
Good. So hold on to that.
Yep.
I'll tell you when to bring it back to me. I like it. Okay, good. Let's say somebody's got a claim about credit card debt. And their claim is that it's, I don't know, what's a good claim? The claim would be it's less than, what do you got, Jeff? You got something for me here, don't you? Let's say it's the claim is it's more than $2,000. Of course, from a confidence interval, we would say no. But the confidence interval isn't the best way to attack claims. You actually have to use what's called a hypothesis test, which kind of makes sense. I want to test somebody's hypothesis. And the thing about the hypothesis test, the reason that it's stronger than a confidence interval for testing claims is it starts with assuming that the claim number here is correct. So I'm kind of testing it from that stage. So I'm saying, say that you're right. Let me go take a sample and see how far it is away from this to see if it looks like you're right or not. And how is distance measured in statistics? Standard deviation, in which actually get more to the point. What uses standard deviations to measure distance? Z-scores. I love it. You kind of with me? Z-scores measure distance. So if I knew that, if I said, if somebody said, let's see, what do I say? On the ESP card test, they said, oh yeah, I can get like 10 right out of 20. And they actually got 9 right. Now they're wrong, but you're close enough, right? You got a little bit of tolerance built in for that, don't you? Like if somebody said, I'm going to take 100 free throws, and I'm going to make 80 of them, and they made 79, and they're going to go, that's freaking close enough. It's too bad for you. You kind of with me? A little bit? I totally lost my train of thought. Where did it keep going? The first thing to realize here is what's important. Let me go right to the important part of that handout, and then we're going to build out from there the other window dressing. It's all necessary, but we're going to go straight to what's important. So this is my claim. So it would look like this here. We know that it's normal enough. And then what was the sample data that we got?
26.
N equals 26. Was X bar was
1329.
29. S was
1621.
1621. Cool. So what's really important here is, like, here's a good example. You guys ever been to the fair? All right. Now, I can't speak from experience, because to tell you honestly, I haven't been to this San Diego fair. But I used to go to fairs all the time out when I lived in Georgia. It's a little different out in Georgia. But almost always, or even if you go to like Busch Gardens or somewhere, or some amusement park, they almost always have somewhere where you can win stuffed bears and all that kind of business. Just doing something silly, throwing a hoop on something that's basically impossible from your angle. Too bad for you. But there's always somebody that says they can guess your weight within so much. So, I mean, if I was going to say I can guess your weight within 5 pounds, that's pretty damn good. Right, what do you say? You have that tolerance built in, but it's established. You have to agree that tolerance is good. If you're outside of that tolerance, no. You didn't get it right. If you're inside the tolerance, you're like, okay, cool. You're good. You got close enough. You with me? So we have to establish what close enough is. Right? And I'm just realizing that my claim is really stupid, but I'm going to try to go back and change it a little bit. Obviously, if my claim was this, then we'd stop right now because we've got a mean below that. So that claim doesn't even live. Well, my claim, let's say my claim is it's less than. Go ahead and change that. That was my bad. I wasn't thinking ahead. So the claim is it's less than $2,000. Then it's not good enough to just say, look, my sample was 1329. That's obviously wrong. You cannot say that. You can't. Why can you not say that? I know that that's less than 2,000, but that's not good enough to say the claim is wrong. There's one very glaring, obvious reason why that's true. Can anybody see that? Where did that 1329 come from? Sample. And samples are notorious for having means that are completely different. They should be close to the real mean. You with me? So this is the key thing. This is the key thing about hypothesis test. If somebody says, oh yeah, like if I said 80% of my students pass this course. That's my claim, 80%. So if I get if 1 year I have 50% of my students pass, that sounds like it's far enough away. You with me? The z-score for that would probably be more than 2, or less than -2, really, because it's down here. You guys kind of with me? So this whole thing is about assuming that this number is right. Is what I see in the sample far enough away to say, no, that's not right? So somebody claimed that they could eat 80 hot dogs. Right? Joey Chestnut's watching. If you follow the world of, I don't really, just every now and again I see in the newspaper, Joey Chestnut eating hot dogs for some reason. If you claim that you can eat 80 hot dogs and you end up eating 50, your claim is busted. I'm sorry. That's way too far away. I don't even have to do statistical analysis for that. You with me? But would 75 be too low? Would 70 be too low? See, there's that little, where the hell is the line drawn? So in statistics, that line can be moved. So very often it depends on, and I'm going to do this a lot today, by the way. We're going to do a little bit, and I'm going to talk a lot. I'm going to do a little bit, and I'm going to talk a lot. So just get used to it. If you're trying to prove to the fire insurance, they just built a new fire station closer to your house, and you're trying to prove that your insurance should go down because the fire trucks now can get to your house quicker. You with me? The burden of evidence is on you. The fire insurance can set what's good enough. So if the old time it took 15 minutes, and now it takes 10 minutes, the fire insurance company gets to say, no, that's not good enough. They set the boundary. Are you with me? Or if you're a football coach and your team sucks, they're all slow as hell, so you want to get somebody fast, so you have people running. You're going to set the benchmark for how fast somebody's got to run that you're going to be interested in them. Are you with me? You set the benchmark that you have to reach to show evidence that you're fast, that you should be on the team. And you see this all the damn time. With every test you ever take, there's some kind of benchmark to reach. Right? Okay, I'm going to pretend like you all shook your head. Okay. So coming back to this. Let's say that what do you think is a decent evidence? So for one thing is, looking at my claim now, which side would I want my sample to show up on to show evidence for this? Just looking at this. Yeah, I want it to show up over there. If it shows up over there, I'm screwed from the beginning. I'm not even going to do the work. That's bad, right? But I want it to show up somewhere over here. So I need to set the benchmark for where that's got to happen. And normally the way that's given to us is in the form of alpha. Alpha really is the area and the tails, or tail if it's one tail test. If it's a one tail. So for 95% confidence level, alpha would be 0.05. There's 5% in the tails. Are you with me? If it was 90% confidence level, alpha would be what? For a 90% confidence level, alpha would be 10%, 0.10. Easy enough, right? How many tail tests is this going to be?
One.
Yeah, because there's one freaking tail, right? I am only interested in less than. It's a one-tail test. Now you understand why this T-chart has area in one tail, area in two tails. It depends on how many tails is in your test. For us, we always looked at two tails, really, because confidence intervals always have two freaking tails. Okay, good. See, it's all coming together. It's crazy. So, a decent benchmark, then, would maybe be something where there's 5% out there. You with me? Especially getting into this, because 5% has historically in this class meant unusual. So if I think the mean is 2,000, and I find a sample that's in there, there's only a 5% chance that that's right. So what's more likely? That's wrong. Are you kind of with me? So I'm saying, assuming you're right, this is what the picture looks like. Assuming that the claim is 2,000 is the mean, it's in there. Assuming that I gotta be a little careful. Assuming that 2,000 is the right number, and we're fighting against that mean, assuming that the mean actually is 2,000, then that's where it would be. If we find a sample that's down there, that's evidence that this is right, that it actually is less than that. So this hypothesis test isn't built off of our sample number, it's built off of some claim. And very often the claim is, we know it from the past to be really this mean. So for example, the gas prices. If it's been $3 and, what the hell is it now? It's been a while since I've got gas. I need some gas. $4? Shit.
Depends on where you buy it, though.
Gotta try to hold on for a while and not get gas. So if it's been like, if it was $3.60 and you think it's gone up, then you would put $3.60 in the middle and you'd think your sample would show up over there. It'd have to show up far enough to show evidence because, again, it's just a sample. The sample being different is not good enough. It's got to be so freaking different that the population is probably different too. I don't know if you guys are with me. Yes?
So, again, what would make that claim true if the sample's within 5%?
If the sample is this far away, and you guys are about to help me with what that would be, that score here. Right? So again, what am I using for this? T-scores or Z-scores?
Z-score.
T-scores, because I have S.
Oh, yeah.
What's the degrees of freedom?
25.
25. And I want alpha to be, how much area is in the tail? 5%, right? I want alpha to be 0.05. So what T-score does that relate to?
0.05.
So remember, be careful, be really careful. 0.05, you have to look at which row on the top, which?
One tail.
One tail. So in one tail,
1.708.
we'll catch up to you. One tail, there's 5%. So if we go down to 25, we get 1.708. You with me? And now you got to be careful. Are there any negative scores on this chart?
No.
Are there any negative T-scores in real life? Hell yes, because they're just the ones that are below the mean. Where are we?
Below the mean.
So what am I actually going to put up here?
Negative
1.708. So be real careful. The chart only knows so much. We're the humans, right? Don't go chart. Tell me. No, we're the humans. We know it's negative.
How did you know it's a negative again?
Just because it's below.
Oh.
It's below the mean. Yes, sir.
So it's 0.05 because we're only using one tail?
It's 0.05 because that's always got to be given to you. They have to tell you at what level. This is called the level of significance. All right, now, I know there's just so freaking much in Chapter 8. The beautiful thing, though, is once we get the idea down, every section has the same exact setup, the same exact idea. The formulas change if you've got T-scores or Z-scores or P-hats, but the setup is the same way. You guys kind of with me? So it's a lot. It's a lot involved. You can tell from the freaking handout. There's a lot of steps to this damn thing. But it's the same damn setup for every section. That's the nice trade-off. So once we get it down, we got all of Chapter 8 down. And actually all of Chapter 9 down once we talk about its big-ass formula. Something to look forward to, yeah.
How do we know the tail?
They have to tell us. Why did I know the tail was here? How did I know that? Because the claim is less than 2,000, right? So I know I have to have it show up over that side. If the claim was it did not equal 2,000, I think it's different than 2,000. What's different mean? It could be either bigger or smaller. That would be a two-tailed test, because it doesn't matter which way your sample goes. As long as it's far enough away either direction, that's proof that it's different. This one's more exact. It says we think it's less. So my sample has to show up here. So that's where my tail goes. Okay, yes, sir.
Yes, if I had to input data 4.708, since the formula actually covers that for you.
The 0.05, right, the 5%?
Right.
The 0.05 coupled with the one tail told us it was 1.708, and it's negative just because I know it's down there.
Right. So, it's a stupid question, but do you actually still have to put it in since the formula actually covers it for you?
Oh no, this is chapter 7. This is different. This is confidence intervals. So now we're doing hypothesis testing, which is different. Yeah. All right. So here's the funny thing. These are the two most important parts of hypothesis test. One is, how far away do I have to get to show evidence? If my sample ends up in here, I show evidence for my claim. If my sample does not end up in there, it's not far enough away, it's not good enough evidence. Are you guys with me? It's a little weird, because on one level, I always have somebody say, well, Jeff, 1329 is less than 2,000. Why are you doing all that shit? All you math people trying to make things. But of course, that's based on a sample. So since it's based on a sample, it's got to be far away from the real me. It's got to be far away to show evidence. If I had the whole freaking population, it just has to be different. I don't care how much. But a sample's got to be far away. Yes, sir?
So it has to be within the 5% time?
So it's got to actually... Yes. That's the easiest answer for that. Yes, it's got to be higher than the 5th percentile in this case. Don't say it like that. That's going to confuse things. But you're right in this case. Okay, so the two most important parts. The first part that's most important is what's evidence? What's far enough away to show evidence? Right? Like the fire insurance company. Well, how much faster do they have to get here? 5 minutes faster? Is that okay? Right? And then you go and get a sample. Then you go and check it. How far away was the sample? So now I'm going to take my sample information and get its t-score. Okay. I love the look on your faces. You're all like, what the hell's going on? Now, here's the z-score formula. And what's got to happen here with standard deviation? What do we have to do with it? It was built into the confidence formula. It's built into this. But what do we have to do before we calculate z-scores or t-scores? So, here I've got my S. Looks all nice, but I've taken a sample. I'm talking about sample means. So what do I have to do with this?
Plug in.
Divide it by square root of n. Right? If I take a sample, and I'm talking about sample means, I have to change the standard deviation. Now don't tell me, oh, but Jeff, that's an S already. No, it has nothing to do with sigma or S. You have to modify. This is the standard deviation for individual credit card debt. I need the one for groups of 26. I have to modify this no matter what.
Oh, yeah.
So here's the z-score formula. Is that cool? That's the new standard deviation down there, right? So back, remember when we did central limit theorem, the first thing we did was change this, and then we threw it into the z-score formula. Here's the z-score formula. Here's the t-score formula. Same damn thing, really.
The new standard.
It's the same stupid thing. You with me? So I desperately want you to understand this. Just because I call it a z-score or a t-score, they both mean the same thing. That's why the formula actually doesn't change. One has a sigma in it, one has an S in it. But they're both freaking standard deviations, right?
Yeah.
Good. So you're just finding the score that tells me how far away my sample is. Our sample is definitely below 2,000, but is it below enough? It's got to be past this mark. So let's get our t-score for our sample and see if it did get that far down. Oh, you guys know? Okay, now you look a little bit more like I want you to. Like, all right, do it. Stop doing this. So t equals, what was x bar? 1329 minus mu always comes from here. That's what we're assuming the middle to be, right? We say, okay, assuming that 2000 is what we're fighting against. 2000 is the middle, and we think it's not there. We're going to assume 2000 is in the middle. So 1329 minus 2000. Now, what have I not done yet? Stupid me. Yeah, I need the new standard deviation, which will be the old one divided by square root of
number of
26.
Yep.
That's what I got to put down there, right? Is that cool? We've done that a decent amount.
It's
Yeah,
317.9.
You change your standard deviation before you put it in there. So I'm saying
317.9.
317.9.
0.9. 042551.
04? Okay, good.
90.
Please understand, we're going to do more and more of these. This is the first run through, and you're picking up whatever the hell you can pick up. We're going to run through it again. All right, just until you kind of get the feel of what's going on. But I really want you to understand the most important part is just how far away do I have to get to show you evidence? And then did I freaking get that far away? It's that simple. Now, the work is freaky a little bit sometimes, but the idea is stupid simple. You got to get here. Did I get there? That's really the heart of a hypothesis test. That's it. This tells you how far you got to get, and then the score you calculate from your sample tells you how far you actually got. And then you say, did I show evidence? So let's see. So that'll be 317.904 on the bottom.
Negative 2.1.
Do it one more time.
The answer is negative 2.11.
1107.
Negative 2.11.
1107. Sure, yeah.
You guys getting that? If you need a calculator, they're up here. Okay. Or everybody else just wait. Somebody's doing it. So, tell me this. Did we make it far enough?
Yeah.
How far did we have to make it to show evidence?
After that mark.
Negative
after that
1.708. How far did we make it?
Past that.
mark. We made.
Negative 2.11, so like right there.
Yep.
So we are farther away than the minimum distance away to show evidence. So does it look like our claim is right? Or does it? We can't say our claim is right. It looks like our claim is right. We found support for this claim. Okay. So that was the minimalistic approach. Believe it or not. That was the minimal. That was 2 steps out of the 5 on the sheet. 2 steps. This is the third step was what's far enough away, and the 4th step is how far away did you get? Yes.
Why do we have to calculate the mean standard deviation?
Because I understand, and I really want this, if anybody's confused about this, just because this is a sample standard deviation is not good enough. This is still a standard deviation for individual debt. I need the standard deviation for groups of 26 debts. You guys got, I have to change it. I don't care if it's sigma. I don't care if it's S. That's not modified. It's still only good for individuals. I need it good for groups of 26 because that's what I have. I have to compare this group of 26 versus all other possible groups of 26 to see if it's far enough away. Maybe. Sinking in. Okay, so what I want to do is with this little bit of knowledge under our belt, I'm going to try to attack this worksheet with you. And then I have a nice blank one for you to try on your own after this one. All right. So does anybody still need that handout from last time that we're going to work on right now? Anybody forget to bring theirs back? Anybody else? Good. Okay. Let's try this dude. All right. Oh yeah, I forgot about that. So this is about, I forgot this was about credit card debt too, so oh well, that seems to be the theme of the day. This is about credit card debt for all Americans, not just college students, right? So this is true data. I looked this up a while back. So 2 years ago, so actually now it's 3 years ago. I used this a year ago. 2 years ago, so 3 years ago was $4,672. Standard deviation of 954. We believe this debt has increased. And actually, credit card debt increasing recently has been a good sign because that means that people are actually going out and buying shit, right? Which is good for the economy. And if you watch South Park at all, you want to keep that God happy. You don't, that's too bad. So the very first step on any hypothesis test is what the hell is the claim? Because that's going to get everything started. It's going to tell me how many tails and all that kind of stuff, possibly. Let's get into that here in a minute. So what do we believe? What's the claim?
It's greater.
Yeah, we believe the debt has increased from what?
From the 2 years ago.
From that. So how do you put that together into a math statement? The other one, sorry.
Sorry about that.
Greater than, the average is greater than.
Yeah, the mean
is greater than the, the average. The previous
4672. I like it. Okay, so now we're going to talk about what the hell's below that. The ho and the high. H-O and H1. Yes. So the HO is called the null hypothesis. Null, if some of you guys realize, is another word for zero or beginning point, right? So null is the starting point. And then the H1 is the alternate. Okay, here's the whole thing about these two things. The H1 will always be the thing that sets up where our tail is. The H1 is the one we can actually show evidence for. Let me say that again. So in this case, that would have been H1. Because we can show evidence for less than, we can show evidence for greater than. We cannot prove equal to. So you can't prove like the average age at Grossmont is 27.3 by taking a sample and the sample is 27.3. Why would that not be proof? Because every sample has a different mean and probably not the same as the real mean. But you can show evidence that it's different from that mean. You can show evidence that it's not equal to. So H1, I think I say this in the notes, the alternate, H1, must have a true inequality, less than, greater than, not equal to. You guys kind of with me? H1 has got to be the guy that says, no, I don't think it's in the middle. I think it's not that. I think it's over there. Either way, I think it's not that. HO always then has to have an equal sign. Greater than or equal to, less than or equal to, right? That'll be HO. So since our claim in this case, which one is our claim in this case? HO or H1?
H1.
Thank God. Okay. So it has no equal sign, so it's H1. Jeff, you can make a, there you go. So our null is going to be the opposite. Those are like two opposing statements. So the null is going to be what?
Greater than.
Careful.
Less than or equal to?
Good. This one's greater than.
Oh,
the
yeah.
opposite is less than or equal to.
Yeah.
I like it. So if we show that HO is wrong, that's also evidence that H1 is right, because those are opposite statements. How are we doing so far?
Yep.
So in one way, this sets up what we're talking about. The first step is, what the hell are you talking about? Will this be a one or a two-tailed test? How do you know? Yeah, this guy greater than is going to be a one-tailed test. In fact, the tail is going to be up. I like it. So it'll be a one
minus.
one-tailed test. How are we doing so far? Just because it was greater than, I need my sample to show up here somewhere. Part B, you knew this had to be in there somewhere. You have to take a second and say why the hell you can use what you're about to use to show evidence. Can we use E-scores, T-scores, or nothing? So look back through the paragraph. What shows that I can use at least one of those things? No. Go take a step back. What's got to be true for either one of those?
All
You have to be normal.
It's got to be normal. What part of this tells me that it's normally distributed or normal enough?
Greater
than 30?
Greater.
Yeah, I got a sample of 74. That's plenty. Right?
Yeah.
So since n is bigger than 30, and what else tells me which one I can use?
Standard deviation.
Where did the standard deviation come from that's given to me? Did it come from my sample?
No.
No, it came from what was known 3 years ago. So this was a little evil. It didn't come from my sample. It came from information about credit card debt in total a few years ago. So that is a population standard deviation, 954. So whoever was saying z-score, you're right. Because that's a population standard deviation. So sigma is known. Since n is greater than 30 and sigma known, we use z-scores.
Z-scores.
How we doing? If n was less than 30, somewhere in the problem I have to say it's normally distributed to begin with. Okay. So here's the part, and I haven't used this word yet. And let me show you why it's called that. So take a step back. Don't even write this down. The claim here would have been H1, right? Because it doesn't have an equal sign. You can do that, Jeff. There you go. So the null hypothesis would have been what? I love it. So, since we got a sample that was way down here, that showed evidence for which one of those? H1, because that's the one that says less than, right? That rejected which claim?
HO.
HO, I love it. So that rejects HO. That's why this region here, that's why this region is called rejection region, because that's the one that says you can reject HO. If I would not have made it in there, I would have failed to reject the HO. Or the null hypothesis, however you want to say that. Okay. So, I'm always worried my dean's going to come into the room right before a second. So the rejection region, we at least know where it is. What side of the mean is it on? We already said that. It was up here. So we know it's up here. What tells me, now we know we can use z-scores. Right, we just figured that out. We can use z-scores. What's the last piece of this puzzle that I need to really be able to determine what that z-score is?
The percent.
Good, the level of significance, the alpha. And in this case, alpha was what?
0.05. 0.05.
Yeah, alpha 0.05. So here's the beauty of the t-score chart again. Some of you guys might know this number already, but I know I have a one-tail test of 0.05. Get out of there, Jeff. 0.05 one-tail test. To go all the way to the bottom, there's my z-score that I want to use. Cool? So this t-score chart is perfect for any hypothesis test because it works for t-scores, obviously. It's a freaking t-score chart. Or z-scores, because z-scores are at the bottom. Kick ass. So everybody see that? I want to use 1.645.
Positive 1.6.
I love it. And I know I'm going to leave it positive because the sucker's up here. So, what I do, just to differentiate here, because that's one z-score, right? And that's the z-score, that's my benchmark. I got to reach that in order to show evidence. Are you with me? And then I'm going to do another z-score next to see where my sample got to, right?
Yeah.
So we got two z-scores kind of floating around. So what I call this guy is z-star. I call that one z-star. It's just me. It's just what I do. I call it z-star. That's the one that comes from my sample because what do? I put a little star on it to see where the hell it is. That's why I call it z-star. You with me? So when I reference z-star, that's what the hell I mean. So right here, what does z-star have to do in a mathematical expression? Tell me what it has to do to reject the null. So what does it have to do visually? Visually, it's got to get in there, right? In the rejection region? So mathematically, how do you say that? I think z-star must be
inside the
if z-star is bigger than 1.645, We can reject the null. Good. It's a better way to say it. We can reject the null hypothesis. Which also means we can do what with the H1? If we get in there. We can never prove anything really, to be honest, but we can show evidence for it. We can support
That it's
H1. So if that one thing happens, since those are opposite statements, we can do those two statements mean the same thing, right? HO and H1 are the opposite. So if I reject HO, that must mean I supported H1. Yes, sir.
H1 is because H1 is
The alternate. The
greater than so it's within that.
Then that means it looks like it's right because it's so much farther up that it looks like it is greater than. So how you doing? Good. Change the look of your face and you're like, I actually understand that. Okay. So that was the step we did here. What's far enough away? So now we know what far enough away is. The next step is just to see, did we make it far enough away? Okay. And then we got to figure out what the hell I mean by that. Well, let's first do that. Go ahead and take a second and see if you guys can collect the sample information and figure out what Z star is. That was what we did here. Well, you got this formula. You know how to do this. Don't forget to do what with your standard deviation? Convert it. Divide it by a square root of n. I like it. So this step is not new. What are you guys getting?
We rejected them.
2.03.
2.03.
2.3, I like it.
We rejected.
So, by itself, that's an easy test. I can see exactly what happened, right? What did happen?
Reject the null
Because their sample was
greater than 1.61.
Be even less mathematical in your answer. Our sample was
Greater.
be even less mathematical in your answer.
It was.
You're a math teacher, man. What are you asking?
It was great.
It was big enough.
Big enough.
Right? It was far enough away from the middle. It was far enough away from the number it's trying to work against. All right, so the claim was it's greater than 4672, and our sample was bigger than that enough. It didn't just have to be bigger than it; it had to be bigger enough. That told me what bigger enough was. So I am bigger than that enough. I'm far enough away. How are we doing? So visually, I could just say, okay, it's about right there. What the hell? It's in there. The p-value is actually, it's kind of funny because I've already got the answer. The main answer to the whole problem is, yes, that sample looks like it rejects the null. It looks like it supports the H1. What we said right here, right? Because Z star was bigger than that, which is what you guys kept trying to tell me, and you're wrong. So what the hell is this p-value? The p-value would be the area of the tail that our z-score makes. So alpha is in the area that this tail is, right? Because alpha freaking gave us this number. So, of course, that's alpha in there. The p-value is the area in our tail. And it actually is the probability that we're wrong, in a sense. It's the probability that we're wrong. So the smaller the p-value is, the less chance there is that we are wrong. And to be a little more direct, that's the probability that we would get that sample even if the mean was right. I really want this to be understood because this is one of the freakiest things to get down. So just because our sample was this far away, does that mean that the mean is definitely not this? Does it mean that it's greater than that? No. The probability that the mean, that we get a sample of this mean, even if this was right, is the p-value. That's the amount that's in the tail of our z star. Holy crap, what the hell did he just say? All right. I know there's a lot. On one level of this is, can you just find the area in the tail of this z-score? That's the p-value. But to interpret it, it's the probability that I would get this even if this is right. Because there's a chance, even if the mean is this, if I could randomly pick people and get a debt up to here, that could happen. It's not impossible. It's never impossible. But it could be so unlikely that what's more likely is this is wrong. That the mean is actually higher, and that would make this a little more likely to happen, because it just freaking happened. So what is the p-value? Can anybody tell me what the picture really is? Let me draw it here. Too much crap in there. So our p-value, I guess you gotta love this stuff, right? Here's the 1.645, so the alpha there was 0.05, right? Our z star is here, 2.03. So what is the area in that tail? So you guys can do this. This is an old question, right? What's the probability that z is bigger than 2.03? That's a section 6.2 question, right? Can you guys get that? There was a shortcut way to get it, or you got to do 1 minus. Well, what do you do first?
1 minus.
1 minus.
Not this. 1 minus the area. So look up the area first. What's the area you get for 2.03?
0.9783. 0.9783? No. 0.9788.
9788?
Yep.
All right. So that would be here, right?
Yeah.
So what's this area here?
1 minus
Yeah.
0.978.
0.0212. So about 2.12%. That's the p-value. That's the p-value. And you're like, what? Okay. That's what you always see in journals when they do a study, in articles when they reference a study. You know, you see these clinical trials and all this stuff, and you always see p-value of something. And if the p-value is small, that's significant. That means that's evidence that something weird's going on. That sample was so far away from what you expected, or what was claimed, or what was normal, or what was last year, that actually it's changed somehow. So the smaller the p-value is, the more evidence it is that something happened. The bigger it is, the less evidence, the more likely it is that nothing happened. It's the same. It doesn't show any significance. Okay, maybe. Maybe not. Yes, sir.
So mu is the mean. Is also the mean of an x bar is the mean of the population.
Yeah. So we're always on this kind of problem. We're always assuming. Look at what the null says. Look what the null says. It says that the mean could be 4672. So what we effectively say is we say, all right, assuming 4672 is the middle. Look what I just did. Right? It's really what we're doing. Assuming 4672 is in the middle. Let's just assume it's there. You've all known people like that. Assuming you're right. What the hell just happened? So assuming it's actually, where's my picture I want? Assuming 4672 is really right in the middle. We just found a sample that is so unlikely to happen. The p-value here was just, where'd it go? 0.0212. Just 2.12% chance it was going to happen. So the sample we got, assuming that this is right, was so unlikely to be gotten that what's more likely is this is wrong. What's more likely is the mean is actually bigger than 4672. And really what's going on is, if I say assuming 4672 is in the middle, so that I think the picture looks like that, and then we get 48, whatever the hell it was, 97, and we say, okay, that's far enough away, so then the picture really should be maybe something more like that, where this is not the mean, but at least it's moved up a bit. You guys see what I'm saying? So it's really testing, is the middle in the right place? If I get a sample that's so far away from what the middle is supposed to be, that can't be the middle. The middle should be somewhere else, probably higher, and that would make that more likely to happen. So if I have a bag of stuff, I should have done this, I didn't even think about it. If I had a bag and I said, there's 80 blue chips and there's one white chip, and you put your hand in and you pick out a white chip, that's pretty damn good evidence that there's more than one, that I lied to you. Are you with me? It's not impossible for him to have picked out the one white chip. But for that to happen, that's really unlikely. What's more likely is I just lied through my teeth, and there's more white chips there, right? If he drops it back in and the next person picks out a white chip, now that's like, okay, you're lying. You've lied to us before. You've probably been lying this whole semester. That explains why this shit is so weird, right?
You're gonna fail
No,
us.
don't give too much away. All right, hopeful. So let's finish this thing out. There's a couple more steps. And then I want to try to show you examples of p-values in articles. And we're going to look online real quick. I didn't look for this, or I should have looked some up, but we'll see what I can find. One last step is, of course, you know this is coming, the explanatory statement of what the hell you just did. All right. So what is your conclusion?
Far enough away from the middle.
So here it goes. You ready? I like that you guys are trying to answer me, and there's actually a very standard answer. So did we find evidence or not?
Yes.
We have found evidence. Good.
Rejected the-
If we didn't get into the rejection region, we would not have found evidence. But we did get in there, so we have found evidence. Now, real quick, since we made it in here, then these statements are true, right?
Yeah.
Which one of those was my claim, the HO or the H1?
H1.
So I want to word my conclusion based on my claim. So which language do I want to use about H1?
H1.
Alternative.
We can support. H1. Don't say we found evidence to support H1. We have found evidence, don't say that. We have found evidence to support the claim that the average credit card debt, let's say mean credit card debt, has increased from 4672. We have found, in fact, let me be a little more, this kind of sucks, but it's too bad. We found sufficient evidence. We found sufficient evidence to support the claim that the mean credit card debt, has increased from $4,672. If we would not have made it in there, we would have said we have not found sufficient evidence to support the claim. Blah, 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 blah. You with me? Freaky, freaky. All right. So let me try to look real quick on... Oh, we got plenty of time. Look at the interwebs and see if I can find a nice article. A really good way to do this is to stay study and then search tools past month. Oh, let's see, I want an article. Here we go. Whoa. That sounds cool. Okay, sorry. Oh. See if they show me what I want. Dorks, they don't show me what I want.
Man,
Yeah, I have to have access. I probably have to pay them money.
Can you guys go through the school database?
What's that?
Can you guys go through the school database?
Here we go. Oh, this has got all kinds of stuff. Ooh, yeah, perfect. All right. So, that might have seemed like a lot of time, but it wasn't much time, right? And if I would have done that for class, I would have actually had an article to look at, but oh, too bad for me. So all I did was type study into Google. I said search within last month. And then I found very quickly, I forgot even what this is about. Light exposure could influence sleep and circadian timing. True. But now, I mean, just scan this really quickly. I knew this was good because I saw all this nifty statistics. And then I saw even better, I saw this. P less than 0.01. So can somebody tell me, without even looking at what the hell it's talking about, what does that by itself mean?
It's less than 1%.
Did they find evidence of something?
Yeah.
Yes, because p-value is very small. It would pass an alpha of 0.01 test, right? And that's why it's called level of significance. That's pretty significant. Yes. So whatever the hell they're talking about there, probably something very strange sounding. The mean light timing was defined as the average of blah, 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 was positively correlated with BMI, body mass index, and midpoint of sleep. And look at this, the connection with body mass index, even more significant. It's less than 0.001. Are you guys semi with me? So to be completely honest with you, the idea of the alpha is sort of not, most of the time it's not there. Because we have no idea where the cutoff should be. When we start a study, we're like, all right, what do you think? I don't know. Let's go get some people and shine light on them and say, go to sleep, right? And then we see. So that's why we always report the p-value, because then anybody else who wants to make up their own benchmark, well, it's got to get past 0.05 for me. Well, then I got past that, dude, so that's good enough evidence for you. But somebody else might say, no, it's got to be better than 0.001. That's not good enough, but that is. Are you guys kind of with me? Then whoever's reading this article can determine for themselves if that's significant or not. And sometimes it's very obvious. That's pretty much for everybody is going to be significant. That, for almost everybody, is significant. Get above this, then it starts to be, some people it's yes, some people it's no. Are you kind of with me? And that's good. You can make up your own mind if it's worth something or not. I love it. So that's why you always see p-value anywhere. If you're any business majors, you're going to be using p-value in some of your studies. Yay! Okay, maybe. All right, maybe. Who's heard of something called the Large Hadron Collider?
Yeah, I've heard of it.
In Europe, there's my geeks. All right, good. My fellow geeks. The Large Hadron Collider, it basically accelerates particles to very fast speeds, and for some of the studies, they smash particles into each other and observe what the hell comes out. So that's how you can kind of see what matter is made up of. Right? So you smash these things together, they explode into little parts, and you say, oh, it's made up of this and this and this and this. But thankfully, there isn't somebody in there actually going like that, because they would die when it killed them. So they have evidence, they have other ways to see it. It's kind of cool.
It's less than 0.1 millisecond, so that they can't even see.
Exactly. So most of the particles, the time that they exist is so tiny that, and obviously the particles themselves are very tiny, so nobody could actually just see them. But very recently, they found evidence. You'll love that. Now this, please understand that you have no duty to understand what the hell exotic hadrons are. There's only one reason I'm bringing this up. Well, there's two. One is you should be aware of this, I don't care who you are. And secondly, they do reference something statistical in their analysis, of course. They're trying to find evidence of existence. They have to have some statistical analysis. Where am I? Blah, 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 blah. Yeah, that's how I found out about it, was from Reddit. Let's see. Is this the one? Let me go straight to the actual paper here. Now, these guys don't use p-value. In science, very often you don't need to. And I'll show you why. Now, there's a lot of stuff on here that's like, okay. So I don't know if you guys have ever heard of quarks, and that's what particles are made of. And of course, you can even break, if you could break it down further. And there's a certain, all right, just stay with me. You're not responsible for any of this physics theory. There's a theory that says certain particles are made up of certain numbers of stuff. So what they just found out was, oh, we just observed something that wasn't made up of what we predicted it to be. That's why it's such a huge thing. It's like, oh, there's something we didn't know. And science loves it when it says, oh, that happened, that's weird. Then everybody in science goes, oh shit, yeah, cool, what the hell? So notice, there's something up here that is familiar to us. Something, not babar. Sorry, let's see. I didn't even see that before. There it is. The significance of the signal is overwhelming. At least 13.9. Can you guys see that symbol?
Yeah.
Sigma. So this is actually 13.9 standard deviation. So this is actually a, what would this be? Is it a z-score? Beautiful. The z-score tells me how many standard deviations. So in science, very often, they still use p. Don't get me wrong. They use p-value. But sometimes you don't need to. 13.9, what would the p-value be for that? Basically 0 to most people. Scientists, it wouldn't be 0. It'd be 0.30 zeros and then a 1. You guys get, so that would be stupid significant. So when you see this, that's all you got to say. 13.9 frickin' z-score. Hello. Right? And they're all high-fiving and trust me, drinking a lot of stuff. Trust me. Anyway, so that was just to see if anybody was at all interested. That's a very interesting, very big thing that just happened in science. But the really good thing for me was I could show you that because there's actually statistical stuff in there. Not the p-value, but at least the z-score. Right? They did a hypothesis test, and that's the z-score they got for their sample. That's really good evidence that what they saw is true. That's evidence that those things exist. It's neat, even if you don't think so. Okay, so here, I want you guys to try. You've got this one as a model, the one we just did together. I want you to try this problem out on your own. Whoever missed today's class, hate himself. And whoever is here today is probably hating himself.
No more hating, yeah.
Or did they
Hating me, that's normal.
or some of them might drop.